This is part 2 of covalent bonding and representing them with Lewis structures. So last time we worked on just drawing them through shared pairs and lone pair dots. And in the two examples we did in part 1, our valence electrons matched the amount of valence electrons in our picture. And we count our valence electrons by pairs. So I usually count them by 2s. For a lone pair, I'm including both dots when I count the 2, and for a shared pair, I'm just counting the line one time when I count the 2, when we are counting electrons. So for bromine, we said there are 14 that are being shared, so we need to only use 14 in our drawing, and we have 2, 4, 6 in lone pairs on the left bromine, 2, 4, 6 in lone pairs on the right bromine, which is 12, and then an additional 2 in the shared pair, that's 14. Now, when we start working with multiple bonds, sometimes we will see that our number of valence electrons in our drawing doesn't quite match how many we counted. Maybe we used too many. And so what we'll need to do is just share additional valence electrons through double or triple bonds as needed. So carbon dioxide is an example of this. Let's start our process by seeing how many available valence electrons there are. Carbon has 4, and each oxygen has 6. Okay, and just like we've said before, we have these spots that need electrons, and because these are all non-metals, they're all going to be asking to gain electrons, and that is why we share. It doesn't work with the transfer method like we did in ionic. Now we need to form bonds. So basically where we have those empty spots, we're going to end up sharing, and that works out because there are 4 on carbon and 4 between the 2 oxygens. However, we'll notice that we have a problem when we try to share all of our electrons because we will end up needing to share multiples. Okay, so we have 4 carbon, 4 valence electrons on carbon, and 6 on each oxygen, giving us a total of 16 valence electrons. If we draw our pictures like before, we will lay and connect the atoms flat on the paper, and then complete our octets with lone pairs. I'm going to surround each oxygen with 3 lone pairs, giving us a total of 8 electrons, 6 from lone pairs and 2 from shared. And then my carbon currently has 4 from shared, so I need to add 2 lone pairs to give it an octet. Okay, so now we're at the point where in the previous examples that we did in part 1, we would be finished. But we have to use exactly the amount of electrons that we counted. That's our first rule. Count and share exactly the molecule sum of valence electrons. The next part of this rule is what we're going to use in this problem. Share with multiple bonds if the diagram exceeds available valence electrons. Let's count how many we used in our drawing. Again, I'm going to count by 2s. 2, 4, 6, 8 on the left oxygen. 10, 12, 14, 16, 18, 20. So I have 4 too many electrons in my drawing. So what I'm going to end up doing is double share between each of my carbon and oxygen. And if you look over at our Lewis structures that we drew over here on the left, you can sort of see that we're going to have to do 2 shares per oxygen to the carbon. And that's what we're going to show with our lines. So our 2 shares are going to have to be from electrons in the carbon to the oxygen. So 2 to each oxygen. They're just going to share. They're not transferring, they're sharing. So the way that we show this in our picture is we are going to take 2 lone pairs that were kind of belonging to each individual atom and then share them in the middle. So we're going to remove some electrons here. So I'm going to take off these 2 lone pairs from oxygen, and I'm going to take off a lone pair from carbon. And now I'm going to share those and put them in a shared pair, still completing their octets, because now this double line is 4 electrons that are contributed to oxygen and to carbon. Remember, a bond, a shared pair, contributes all of its electrons to both atoms. It's not like split in half, they both get 4. So our octets are still complete, but we still have a problem. We're using 18, and as a result, we're just going to fix our right side carbon and oxygen bond the same way we did on the left side. Take these lone pairs that were just, exclusive to carbon and oxygen, and now we're going to share an additional pair, making another double bond. And now we're using the correct 16 valence electrons. 2, 4, 6, 8, 10, 12, 14, 16. Happy day. All right. As we start using multiple bonds, sometimes the picture is harder to kind of visualize. So you can always start by just drawing it flat and then taking away lone pairs and sharing additional bonds until you reach your desired valence electron count. Lastly, we're going to work on a polyatomic ion. This is phosphate, which has 1 phosphorus, that's 5 valence electrons, 4 oxygens, and then it has a -3 charge. So again, if you will go back up and look at our rules where it's talking about counting our electrons, there's a note here that says when drawing polyatomic ions, negative charge is number of extra electrons and a positive charge is the number of deficient electrons, or electrons you take away. In this case, we have negative charge, so I'm just going to add 3 electrons down here, part of our pool of electrons that can be shared. So again, all of these are nonmetals. They're all going to be wanting to take electrons if they were in ionic compounds, so we have to share. Let's add up all of the electrons available to share. We have 5 in the phosphorus, 6 in each oxygen, so that would be 29 plus the additional 3, which is 32. Okay. And then we're going to lay our atoms flat on the page, or put the one that's different in the middle and surround it kind of like a T. Okay, then we're just going to connect them, so we have to share, and surround with lone pairs to complete the octets. In the middle, phosphorus already has an octet because it's sharing 2 from each oxygen, giving it 8 already. So now we just need to put 3 lone pairs around each oxygen. So we'll have 6 electron dots and a shared pair for each oxygen, giving it 8 in its octet. So now our octets are full. Let's check to make sure we used our 32 and we don't have too many dots and need to kind of share extras. Let's check. So I'm going to count by 2s, starting on this left oxygen. 2, 4, 6, shared pair 8, 10, 12, 14, 16, shared pair 18, 20, 22, 24, shared pair 26, 28, 30, 32. So I do have all 32 and all of my octets are complete. So my 2 rules are satisfied. One little thing that we do with polyatomic ions, we just draw brackets around it and add the charge in the upper right hand corner, just to show this is a polyatomic ion, which was given 3 extra electrons in its structure. So that is how we go about drawing polyatomic ions. If you have a negative charge, you're adding extra electrons. If you have a positive charge, you're going to take away some electrons. And the only case where that would be in ammonium, so you would just take away 1 electron when working with ammonium. If you ever have a structure kind of like carbon dioxide where your picture has too many electrons, just share some more bonds. You can go up to triple bonds if needed. But remember, if you tried to do triple bonds, you got to double check that you don't have too many on your octet. Now this one, it wouldn't even work that way. But if you were to try, and I put a 3rd bond on this left side, now I have 10 electrons on carbon. So just be aware of that as you do double and triple bond, that you're not overloading the central atom. and that you have an octet, not too many, not too little, for each of your atoms. Following those two rules, count and share exactly the sum of the valence electrons, doing as needed with a polyatomic ion or multiple bonds, and complete the octet for every element in the molecule using those lone pairs. Everything needs 8, except for a couple of weird elements. Hydrogen is fine with 2, so you'll never really put lone pairs on hydrogen, you'll just be sharing pairs, and that makes it content and stable. And boron is stable with 6. There's some practice pages, page 4 and page 5. Page 4 is like the examples we did in part 1 with single bonds and filling octets with lone pairs. Then there's a couple where you will kind of find the mistakes. And then on page 5, now we're going to start looking at kind of what we did in part 2 with possible double bonds and triple bonds and polyatomic ions.